Your AI tools are sending emails, processing files, and handling sensitive operations. But how do you track who's making those requests or correlate them across distributed systems? You'll see how to access client-provided metadata in FastMCP, like user IDs and trace IDs, to add observability and context-aware logging to your tools without changing their core logic. The pattern uses the request context meta object to safely extract and use client-supplied data for debugging, auditing, or personalized behavior.
At MCP tool. Def send email to SDR subject, SDR body, SDR CTX context, SDR. Send an email logging metadata about the request. Hash access client provided metadata. Meta equals CTX, request context meta. If meta, hash meta is accessed as an object with attribute access. Userid equals meta userid if hasheader meta. Userid, else none. Traced equals meta traced if hasheader meta. Traced, else none. Hash use metadata for logging, observability, etc. If traced, log with trace. F sending email for user userid, traced. Hash send the email. Return F email sent to.
This demonstrates the context injection pattern for building request-aware services. The code shows how FastMCP injects a context object into tool functions, providing access to request metadata, logging, and observability features without explicit dependency passing. The distinctive aspect is how metadata, like user IDs and trace IDs, become first-class citizens in your function logic, enabling cross-cutting concerns without polluting your core business parameters. The pattern works by treating context as an ambient dependency that's automatically available during request processing. Your tool functions declare what they need via type hints, while FastMCP handles the injection at runtime. This creates a clean separation. Business logic stays focused on its primary task, while framework concerns like logging, tracing, and client metadata are handled orthogonally through the context object. This approach solves the problem of request scope data access in distributed systems. Instead of threading metadata through layers of function calls or relying on global state, you get a scoped, type-safe way to access request information. It's particularly valuable for observability-heavy applications where you need to correlate logs, traces, and user actions across service boundaries, without coupling your core logic to specific transport mechanisms. Let's break it down.
At MCP tool. Def send email to SDR subject, SDR body, SDR CTX context, SDR. Send an email logging metadata about the request.
The @MCP tool decorator marks this function as an AI callable tool. FastMCP uses the type hints and docstring to auto-generate the tool schema, including parameter validation and documentation. All tools must accept a context parameter for logging, progress reporting, and metadata access. This pattern ensures consistent observability across all AA-triggered operations.
Hash access client-provided metadata. Meta equals CTX, request context meta.
This extracts metadata from the context object, which contains client-provided request details. FastMCP tools should use this pattern to access additional request context, like user IDs or trace IDs for logging and observability.
If meta. Userid equals meta userid if hasheader meta. Userid, else none.
This safely accesses optional metadata using Python's hasheader pattern. It checks for userid before access, preventing attribute error if the field doesn't exist, while defaulting to none when missing. This defensive approach handles dynamic metadata structures where fields may be absent.
Hash use metadata for logging, observability, etc. If traced. Log with trace. F sending email for userid. Traced.
This implements distributed tracing for observability. When a traced exists, it logs the email event with that ID, enabling cross-service request tracking, critical for debugging production workflows.
Hash send the email. Return F email sent to.
This placeholder return simulates the email sending operation, returning a confirmation message with the recipient address. In production, you'd replace this with actual SMTP client code or an email service integration. The pattern keeps the example focused on metadata handling while showing the expected output structure. Metadata-aware tools. The context object in FastMCP transforms simple functions into metadata-aware operations, enabling client-specific behavior without changing the core function signature. Client metadata is always optional, so your code must handle cases where meta is none or attributes are missing. Design tools to be useful with or without metadata, then enhance them with contextual awareness.
The tool that knows nothing about its caller serves every caller perfectly.